Hello, my precious friends. I really hope that you are doing great. Welcome to our today's class. It is our fourth and last lesson on the 10th topic of Form 3 work, which is called gas laws. As usual, let me commence by giving the quote of the day, which states that opportunities don't just happen. You have to create them. We shall discuss that quote at the end of our class today. So today we're looking at gas laws and kinetic theory. So basically we'll be explaining how the kinetic theory of matter can be used to explain the gas laws. So let's start with the first law, which was the Charles law. So we look at the Charles law and kinetic theory. So basically the Charles law stated that the volume of a fixed mass of a gas is directly proportional to the absolute temperature, that is whenever pressure is kept constant. So an increase in temperature will always increase the kinetic energy of the gas molecules, thus making those particular molecules to move away from each other. So this increases the intermolecular distances between any two successive molecules, hence increasing the volume. So it is important to remember that volume is defined as the amount of space occupied by a body. So suppose these are our gas molecules which are in a given container, this particular container. So at 25 degrees Celsius, you can see that the intermolecular distances between any two molecules is actually very small. That is, the molecules are closer to one another. That is at room temperature of 25 degrees Celsius. However, if you heat this particular gas, or if you increase the temperature of this particular gas, the molecules of the gas are going to gain kinetic energy. Remember, kinetic energy is the energy in motion. So that means that these particular molecules will now have the ability to move from one point to another. So when the molecules gain kinetic energy, they will start moving away from each other. And of course, as they move away from each other, that means they are increasing the intermolecular distances between any two particles. So at a higher temperature of, let's say, 90 degrees, the molecules will move away from each other because they have kinetic energy, hence increasing the intermolecular distances between any two molecules. So whenever intermolecular distances are increased, that simply means that that particular gas is going to occupy a larger space, and we said that the volume is the amount of space occupied by a body. Therefore, the more the space occupied, or the larger the intermolecular distances, the more the space that particular gas will occupy, hence the larger the volume. So essentially, an increase in temperature increases kinetic energy of the molecules, making the molecules to move away from each other, hence increasing the intermolecular distances. Whenever intermolecular distances between any two successive molecules is increased, actually the volume increases because that gas usually tends to increase. It tends to increase actually its volume, or the amount of space that it occupies. Then two, we look at the pressure law and kinetic theory. So essentially we said that the pressure law stated that the pressure of a fixed mass of a gas is directly proportional to absolute temperature whenever volume is kept constant. So in this case, we are going to use containers that have a fixed volume. So when a gas is heated, or when its temperature is increased, its molecules are going to gain kinetic energy, and hence the molecules will move faster away from each other. So if the volume of the container is constant, then it means that the molecules will bombard, or they will collide with the walls many more times per unit area, and with a greater momentum. So of course, the total rate of change of momentum will therefore increase. So the resulting force per unit area, which is actually pressure, will actually increase. So basically, you can see our first container here having the same volume with our second container. But the first container is at a lower temperature of, let's say, 10 degrees Celsius, or at room temperature. Therefore, the molecules are just closer to each other because actually they do not have any kinetic energy that will help them to move away from each other. However, when you heat the gas in that particular container, the temperature of that particular gas is going to increase. And when the temperature of the gas increases, it simply means that the molecules will gain kinetic energy, hence moving away from each other. So as the molecules move away from each other, they actually collide with the walls of the container, because remember, we are keeping volume constant. So here, molecules don't have any kinetic energy, therefore they'll just remain at a state of rest, or if there is any movement, it will just be some slight movement. But for this case, when the container is heated to 80 degrees Celsius, the molecules will gain a lot of kinetic energy, hence their rate of motion will actually be very high. So as the molecules move, because they have kinetic energy, they collide with the walls of this particular container, and they also collide with each other. So those collisions or those bombardments of the molecules with each other and with the walls of the container per unit area, that is what we are calling the pressure. So the more the collisions or the more the impact of the molecules with the walls of the container and the more the collision of the molecules also with each other, that means the pressure within that particular container is going to increase. Therefore, an increase in temperature will lead to an increase in pressure when the volume or when the size of the container is actually kept constant. Then we look at the Boyle's law and kinetic theory. So basically, Boyle's law stated that the pressure of a fixed mass of a gas is inversely proportional to the volume, that is whenever temperature is kept constant. Therefore, we are going to keep temperature constant, meaning that the molecules will not gain any kinetic energy, but we are going to reduce the volume of that particular container. So at a constant temperature, the average kinetic energy of molecules is constant, because what makes molecules to increase in kinetic energy is actually heating them or increasing their temperature. So when temperature is kept constant or when temperature is not increased, it means that also the average kinetic energy of the molecules is going to remain constant. So if the volume is halved, so when you halve the volume of the container, it simply means that the number of molecule impacts or collisions per second per unit area of that is of the wall surface will be doubled. Thus the pressure is also doubled. So when temperature is kept constant, you can see that the molecules have a lot of space. Therefore, the probability of these particular molecules colliding with each other and also with the walls of the container are very, very low. However, when you reduce or when you have the size of the container holding those particular molecules, and remember we are keeping the mass of the gas constant, so the mass of the gas is actually constant, but we are reducing the volume of the container holding that particular gas. So when you reduce the volume of the container, it simply means that the molecules will now be closer to each other, and they will also be very closer to the walls of the container. So the closer the molecules, the more the impact or the more the collisions with each other and also with the walls of the container. So those collisions is what we are calling the pressure. So the more the collision or the impact or the bombardment of the molecules with the walls of the container, the more the pressure. And for this case, because the molecules have larger spaces or the volume is large, the probability of the molecules colliding with each other and with the walls of the container will be very low. Hence, the pressure in this case will be very low when the volume is large. But for this case, when the volume is small, the pressure will be very high, because the probability of the molecules colliding with each other and with the container, with the walls of the container will be very high. So those impacts or those collisions is what is constituting what we are calling the pressure, or the pressure will actually be doubled. Next, we look at the limitations of gas laws, and the main limitation of gas laws is that at very low temperatures, most gases will not obey the gas laws. The reason being, at very low temperatures, most gases will actually condense to form liquids, and some can even form the solid. So at very low temperatures, most gases will not obey the gas laws because they condense to form liquids, and some can also form the solids. Therefore, there are only ideal gases which can actually perfectly obey the gas laws. Therefore, an ideal gas is defined as a gas that obeys the gas laws perfectly. So, of course, ideal gases do not exist in real life. So, they are just imaginary gases, because actually at very low temperatures of even below 0 degrees, actually most gases will not exist, because they will be liquefied or they will form liquids, and some can also solidify. Next, we look at the equation of the state, which is derived from the Boyle's law and the Charles law. So remember, the Boyle's law required that pressure should be inversely proportional to volume. So that also means that volume can also be inversely proportional to pressure. Then the Charles law required that volume should be directly proportional to absolute temperature. So I want to combine these two equations to form the equation of the state. So because volume is constant in this particular case, I'll just pick one value of the volume. Then we know that volume is inversely proportional to pressure. Therefore, volume is inversely proportional to pressure. But at the same time, from the Charles law, volume is directly proportional to the absolute temperature. So also volume is directly proportional to the absolute temperature. So when I combine these two equations, because volume is common, I'll just pick one value of the volume, then I multiply the value of the reciprocal of pressure and the temperature. Therefore, volume is inversely proportional to pressure. At the same time, volume is directly proportional to the absolute temperature. Then I'll just multiply the values on the numerator. So 1 multiplied by T, you'll just get T. Therefore, V will be directly proportional to T divided by the pressure. Then, of course, to remove the proportionality simple, I simply introduce equal signs with a constant. So my constant in this case, I'm using K, then of course with equal signs. So this will be V is equals to K multiplied by T divided by P. Therefore, to make K subject of the formula, I'll just multiply both sides by the reciprocal of T over P. So if I multiply both sides by the reciprocal of T over P, I'll simply have pressure times volume divided by absolute temperature being equal to K. And of course, K is a constant. So because K is a constant, that simply means that if you take the product of pressure and volume divided by temperature at one point, or maybe at a point A, it must be equal to the product of pressure and volume divided by the temperature at another point, maybe at a point B. Therefore, from this equation, it simply means that P1 V1 over T1 must be equal to P2 V2 over T2, where P1 is the pressure at the first point, V1 is the volume at the first point, T1 is the temperature, that is in Kelvin, at point 1. Then P2 is the pressure at the second point, V2 is the volume at the second point, then T2 is the absolute temperature at the second point. Therefore, let's look at an example which involves application of this formula. So our example is that a gas occupies a volume of 200 cubic centimeter. So that is our V1, which is 200 cubic centimeter, or volume at point 1, at 25 degrees Celsius. So that is our T1. Again, we said that this formula can only work if the temperature is expressed in the absolute scale or in Kelvin. Therefore, our T1, to convert it into Kelvin scale, I'll simply take 25, then I add 273, which is equals to 298 Kelvin. And pressure of 7.6 times 10 power 2 millimeters of mercury. So this is our P1, or the pressure at point 1. So remember, 10 power 2 simply means 10 times 10, which is 100. So if you take 7.6 times 100, you'll simply obtain 760 millimeters of mercury. So we are told that state the volume it will occupy. So they want V2, or the second volume, if the temperature is reduced to, so this is the final temperature, negative 23 degrees Celsius. Again, we convert it into the SI unit, which are the Kelvin. So we'll simply take negative 23 plus 273, which gives us 250 Kelvin. And pressure to 0.75 times 10 power 3. So this is the final pressure, that is the P2, is 0.75 times 10 power 3 millimeters of mercury. So of course, 10 power 3 simply means 10 times 10 times 10, which is actually 1,000. So 0.75 times 1,000, you'll obtain P2 as 750 millimeters of mercury. So they want us to find V2. So we just apply our formula that P1 V1 over T1 must be equal to P2 V2 over T2, where T must strictly be in Kelvin. If you use the temperature when it is in degrees Celsius, you won't find the right answer. Therefore, our P1 is 750, that is 760 millimeters of mercury, multiplied by our V1 is actually 200, divided by our T1. Our T1 is 298 Kelvin, must be equal to our P2 is 750 multiplied by V2. V2 is the unknown, then divided by T2. Our second temperature, T2, is 250 Kelvin. Therefore, if I do cross multiplication, I'll have, so the 250 will multiply with the numerator on this side, so that I have 760 times 200 times 250 being equal to this denominator, 298, will multiply by the numerator on the right hand side. So that will be 298 times 750 times V2. Therefore, I want to multiply. So this 750, that is 760 times 200 times 250, you'll get 38 million. Then 298 times 750, you'll get to 23,500. Then, of course, times V2. So I want to divide 223,500 on both sides, so that I remain with V2, or so that I make V2 subject of the formula. Therefore, V2 will be 38 million divided by 223,500. So if you find this quotient, you will find 170 10 over 447, which is approximately 700 and which is approximately 170 cubic centimeters. Next. Our second example reads that a fixed mass of a gas occupying 4 liters, so that is our initial volume is 4 liters, at 27 degrees Celsius, that is our initial temperature. So 27 to convert into Kelvin, we simply add 273, so it will give us 300 Kelvin, is compressed at a constant temperature until the pressure doubles. So if we let our initial pressure, that is P1, to be X, then for the pressure to double, it means that our final pressure will be 2x, that is the double of x, which is 2x. Then it is then cooled at a constant pressure until its volume is halved. So that simply means that if our initial volume was 4 liters, then the final volume will be a half of 4 liters. Therefore, our V2 final volume will be a half of the initial volume, which was 4 liters. So a half of 4, you'll just get 2 liters. So we are told to determine the final temperature of the gas, then we leave our answer in degrees Celsius. So we'll just use the combined gas equation or the ideal gas equation, which is P1 V1 over T1 must be equal to P2 V2 over T2. So our P1, that is the initial pressure, we let it to be X, so that will be X. Our V1 is 4 liters, then divided by our T1 was 300 Kelvin, is equals to P2, our second pressure, is double the initial pressure, which is 2x, because our initial pressure was x. Therefore, for it to be doubled, it will be 2x. So our final pressure is 2x times V2. The second volume it was a half of the initial volume because the volume is halved. Therefore, a half of 4 liters is just 2 liters. So times 2, then divided by the final temperature, T2, which is just the unknown T2. So if I do cross multiplication, I'll have x multiplied by 4, then times T2. So I'll have x times 4 multiplied by T2 being equal to 300 will multiply by the values on the numerator, that is 2x by 2. So I'll have 2x times 2 being multiplied by 300. Of course, x times 4, I'll just get 4x, then times T2, I'll just get 4x T2 being equal to 2 by 2, I'll just get 4. 4 times 300, I'll get 1200, then of course times x, so this will be 1200x. If I make T2 subject of the formula, I'll simply divide both sides by 4x. Therefore, T2 will be 1200x divided by 4x. Of course, x and x will cancel out. 1200 divided by 4, I'll just get 300 Kelvin. So again, Kelvin, because T1 was also in Kelvin. But they want us to leave our answer in degrees Celsius. So we know that to convert temperature in Kelvin to degrees Celsius, you subtract 273. Therefore, temperature in degrees Celsius will be 300 minus 273, which gives us 27 degrees. That is in degrees Celsius. Lastly, I have an exercise that I recommend you should try at your own free time to gauge the understanding of the questions that you have done. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that opportunities don't just happen, you have to create them. So the quote is reminding us that nothing will be handed to us freely. Every opportunity you get in life comes at a cost. So the big question is, are you willing to pay the cost? For example, the cost of greatness entails hard work, sacrifice, commitment, consistency, and patience to wait for the results that you've been working for. Therefore, it is okay to hope for better opportunities in life, but make sure that you are doing something productive while in the process of hoping. And lastly, recall that one opportunity used wisely can change your life dramatically. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. If you know any student or anyone that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy. Thank you very much for the support that you have given me throughout this Form 3 work. So this marks the last lesson under Form 3 work. So in our next lesson, we'll be starting Form 4 work. Thank you very much for the encouragement. Thank you for the positive comments that I've been receiving from you throughout covering the whole of this Form 3 work. Until next time, this is Kind Tuition Academy. Thank you very much.